Okay, I'd like to finish up section 11.2 in this video here. So we're on these problems here. We're going to determine if the series converges or diverges. Okay, so there's only three kinds of tests that we know so far, and we're going to learn a lot more tests. Okay, so the first thing is that we have a geometric series. Okay, and then there's the divergence test. The divergence test is really important, okay? It says that if the limit of a sequence is not 0, as n approaches infinity, then the series is divergent, okay? And then we also looked at a telescoping series, okay? So let's see, let's take a look at this example. We got the summation as n equals 1 to infinity of 1 divided by 1 plus 2/3 to the n. Okay, now that's not a geometric series, right? Because I'm not in the form a times r to the n. A telescoping series is not going to work also. Now, if I find the limit as n approaches infinity of the sequence, 1 divided by 1 plus 2/3 to the n, well, let's see, 2/3 to the n, that would be 0 as n approaches infinity because the denominator is bigger than the numerator, right? So the denominator is going to grow faster than the numerator. So the limit as n approaches infinity of 2/3 to the n, that'd be 0. 1 divided by 1 is 1. That's not 0, okay? And so you're going to have a divergent series by the divergence test. Okay, let's try another one here. So what if we had the series given by the sum as n equals 1 to infinity of the arctangent of n? Okay, well, if you look at the graph of the arctan curve, that's the one where there's two horizontal asymptotes. You got one at pi over 2 and negative pi over 2. And the curve is in quadrants 1 and 3, approaching those two asymptotes. So the limit as n approaches infinity of the arctangent of n, if we head out towards infinity, we're getting closer and closer to pi over 2. Okay, pi over 2 is not 0. So you're going to have a divergent series by the divergence test. Okay. Here's another example. So what if you had the series given by the sum as k equals 1 to infinity of cosine of pi over 4 to the k power. Okay, cosine pi over 4, that's 1 over root 2. And so I'm really looking at the series given by the sum as k equals 1 to infinity of 1 over root 2 to the k power. Now, this looks very much like a geometric series. Now, I have to make sure I'm in geometric form, though, before I use the formula, okay? So I need to be in the form a times r to the n minus 1. N is starting at 1. Okay, so I want r to be the power n minus 1. So if we go ahead and factor out a 1 divided by root 2, then we got 1 divided by root 2 times 1 divided by root 2 to the k minus 1. K is going from 1 to infinity. Okay, now I'm in the form that I need to be in, a times r to the k minus 1. And so now I can use the formula for a convergent geometric series. So that's a divided by 1 minus r. A is 1 over root 2 divided by 1 minus r is 1 over root 2. 1 over root 2 is less than 1, so I know that this series is going to converge, right? And, okay, in the denominator there, if we go ahead and rationalize the denominator, 1 is the same as root 2 over root 2. So I got root 2 minus 1 divided by root 2 in the denominator. If I flip the denominator, then these root 2's will cancel. Okay, and I'm looking at 1 divided by root 2 minus 1. So if I add up all infinitely many of these terms, the grand total would be 1 divided by root 2 minus 1. Okay, so let's take a look at another example. What if we had the series, which is given by the sum as n equals 1 to infinity of 5 divided by 3n minus 2 divided by n times n plus 1. Okay. Now, when I'm subtracting two things in a sequence part, I can split up the sum into two sums if I want to. Also, I can bring constants out if I want to. Okay, so 5 is a constant, 2 is a constant on that second summation. So I got 5 times the summation as n equals 1 to infinity of 1/3 of the n minus 2 times the summation as n equals 1 to infinity of 1 divided by n times n plus 1. The first series is going to be a geometric series that will converge because 1/3 is less than 1. Okay, now I need to make sure I'm in geometric form though before I use the formula. Okay, so I'm starting at 1, and the sequence part needs to be in the form a times r to the n minus 1. I'm not in that form yet. So if we go ahead and factor out a 1/3 from that, I'm looking at 1/3 times 1/3 to the n minus 1. 1/3 is a constant that can come out of the series. So I'm going to have 5/3 times the summation as n equals 1 to infinity of 1/3 times n minus 1, and I'll go ahead and use the formula there on the next line. Now this series is one that we have already seen back in, so that was the, let's see, the second problem, or yeah, so the second problem, let me just use partial fractions here. 1 divided by n times n plus 1, that's the same as a divided by n plus b divided by n plus 1. I've got two linear factors there. So then if I multiply the bottom by n times n plus 1, the n's will cancel in that first part, so I got a times n minus 1 plus b times the n plus 1's cancel on that second part there, so I got plus b times n. Or that'd be a plus b times n plus a equals 1. And match the coefficients. I don't have any n terms on the left, so a plus b would be equal to 0, and a is 1. If a is 1 and a plus b is 0, then b is negative 1. Okay, so this series here, the sequence part, I can rewrite as 1 over n minus 1 over n plus 1. Okay, but we have already seen this series before. That was the second problem that I had shown you in section 11.2. So here's 11.2, right? And that's the telescoping series. So this series converges to 1. Okay? Let's see. So I got 5/3 times a is 1 divided by 1 minus r is 1/3. So 1 minus 1/3. And then minus 2, that's in front of the series there. 2 times the summation as n equals 1 to infinity of 1 over n minus 1 over n plus 1. That's 1, I said. Okay, and that's from the second example in this section. You get 1. So then when we simplify this, we get 5/2 minus 2, or 1/2. Okay, so in other words, if I add up all infinitely many of these terms here, the grand total would be exactly 1/2. Okay. Here's I like this problem on page 750, problem 93 in the book. It's a two-part problem. We're just going to do part B here. But it's a two-part problem for what's called a Cantor set. Okay, so a Cantor set is basically where you're starting with the interval 0, 1, and you're removing the middle 1/3 interval each time. Okay, so that's going to leave the two intervals 0 to 1/3 and 2/3 to 1. Okay, and then if you remove the middle 1/3 of those two intervals, then and continue to do that infinitely many times, then the numbers that would remain are called numbers in a Cantor set. Okay, we're just going to do part B, like I said. And it says the Sierpinski carpet is a two-dimensional counterpart of the Cantor set. It is constructed by removing the center 1/9 of a square of side 1, and then removing the centers of the 8 smaller squares. So I got removing the center 1/9 of this, the 8 remaining squares here, and so on. The figure shows the first 3 steps of this construction. Okay, and what I want us to do is, in part B, we're going to show that the sum of the areas of the removed squares is 1. Okay, so if I continue to do this, where I'm removing the center 1/9, that implies that the Sierpinski carpet has an area of 0, which is kind of weird. Well, let's see. So I'm going to start by removing the center 1/9. So I got 1/9. And then I'm removing 1/9 of the 9 squares. So 1/9 of the 1/9 means 1/9 squared. And I've got 8 of those squares that I'm removing. So 8 times 1/9 squared, that'd be the next term. Now, this term here is 1/9 of this group, which is 1/9 of this group, which is 1/9 of this group. So 1/9 cubed. And then I got 8 of these squares that I'm removing. And I'm removing all of these that are around the center. 8 squared is 64. Okay, so the next term would be 8 squared times 1/9 cubed, plus 8 cubed plus 1/9 to the 4th, plus 8 to the 4th times 1/9 to the 5th, plus etc. Okay, so that's what I'm doing. Okay, and 1/9 is in common to all infinitely many of these terms, so let's go ahead and factor that out. The leftover then would be 1 plus, I got 8 left over up top, so 8 divided by 9, so I'm removing 1/9 there. It'd be the next term. Then plus 8 squared divided by 9 squared, I'm factoring out a 1/9. Then plus 8 cubed divided by 9 cubed. Again, 1/9 is out front there. So then let me switch over to summation notation. So I got 1/9 times this sum. Okay. And this is a geometric series. So n is going to start at 0 and go to infinity. The r value is 8/9. So let me just check that I'm getting each term here. So when n is 0, anything to the 0 power is always 1. Okay, 1/9 is in front of the whole thing there. So that's where that comes from. Anything to the 0 power is 1. When n is 1, I get 8/9. When n is 2, I get 8/9 squared. When n is 3, I get 8/9 cubed, plus etc. I'm heading out towards infinity. Okay, and now this would be a geometric series. So I'm in the form a times r to the n. I'm starting at 0, so that looks good. And now I can use the formula. A is 1/9 and r is 8/9. 1/9 divided by 1/9 would be 1. Okay, so if I were to continue to remove the center 1/9 of each of these squares, I'm removing an area of 1. Okay, and that's like you've removed the whole carpet there. Okay, so the area of the Sierpinski carpet in its entirety is an area of 0, is what we're saying there. Okay. All right, so here's the problems that I'd like you to look at in section 11.2. 11.2 is really important, and we're going to continue to see geometric series, for a lot of these sections in chapter 11 there. So be sure to definitely look at the homework problems. Okay, and I'll start till 11.3 in the next video.